Good morning, everyone. Today I'm going to talk about our work, atomic generation of high-performance inference kernels for graph neural networks on multi-core systems. Graph is made up of vertex and edges. It's a natural representation for many real-world applications. For example, in social network, every person is a vertex, and the connection between the two persons is an edge. In code analysis, taking every statement as a vertex, the control flows between them as an edge. You can get a control flow graph. Graph can also be found in many other applications such as map and the internet communication network, as shown in the slides. In recent years, graph neural networks are getting more and more popular. The basic idea of them is to apply deep learning method on graph data structure. First, we have input data and the initial embeddings associated with vertices and edges. Then the input data will go through a series of graph convolutional layers, similar with traditional deep neural networks. At last, GNN will output new embeddings incorporating graph structure information. The output of graph neural networks can be used in many applications, such as social networks, mining, recommender system, and molecular analysis. The computation in each layer of graph neural networks follows a masked passing paradigm. That is, each vertex gathers the feature vectors of all its neighbors and the associated edges. Apply the operations such as matrix multiplication and combine the result with its own feature to produce a new feature vector for the next layer. Here we use graph convolution network as an example, which performs the weighted sum aggregation on all neighbors' features. This formula shows the computation happened in each layer of GCN. Before we talk about our work, let me first explain the motivation of this paper. There are two classes of existing solution can be used for graph neural network inference. On the one hand, we have seen a steady development of high-performance graph processing systems, such as Libra or Kernels. While it is possible to utilize this system to produce high-performance kernels for GNN inference, their low-level programming interface lack the support of neural network operations, making it harder to programming graph neural networks. On the other hand, there have been recent attempts of GNN frameworks, such as DGL, PyTorch geometrics. They are designed specifically to support graph neural networks. They provide interfaces that are easy to programming GNN, but they rely on general tensor operations, which will lead to poor performance of inference. So in this work, we use a new compiler-based approach which can automatically generate high-performance kernels for GNN inference to handle huge graphs while offering a set of easy-to-use API to the users. Here, I will talk about the four major components of our framework. The first is the interface. We propose a new programming model with 3 user-defined functions for the model definition. Then we use data flow graphs as the intermediate representation for representing GNN models based on the user-defined functions. After that, a code generator will lower the intermediate representations into C++ code by traversing the nodes in the data flow graph. At last, we also make use of a couple of optimization techniques to improve the memory and the runtime performance. Our ACG model consists of 3 user-defined functions. The first one is called apply. It is used to define the operation on the feature matrices of vertices or edges before traversing the input graph. For example, in GCN, it can be used to define the matrix multiplication between the feature and the weight parameters as shown in the red box. And in the code would be like this. Only one line of code is needed. The second user-defined function is called compute, which declares the operation defined on each edge to calculate the message to be passed. For the example of GCN, it could be used to define the computation before the sum operation as shown in the red box. The code first defines how to calculate the message and then return it. The last user-defined function gather is used for defining how to aggregate all the message coming from the edges of a vertex. For the GCN, this function is responsible for the sum operation and the activation function shown in the red box. In the actual code, the messages are first reduced into a single feature vector using sum operation and then applied with the relu activation function. At last, the function returns the result, which is the final result of GNN layer. After the user-defined functions have been defined in the interface, they do not actually execute the computation when running them. Instead, they will build the data flow graph IR that represents the graph neural network model. Each graph IR has input tensor, and this tensor goes through a series of operations, and finally they become the output. In the slide, we use blue for the input tensor, green for the operation, and yellow for the output tensor. This IR is the input for the following code generation phase. After generating the IR in the previous step, we use a C++ code generator to generate high-performance C++ code for the GNN inference. The code generator starts with a C++ code template with a basic graph traversal procedure, which is parallel for each vertex in the graph, aggregating the message from all its edges and then return the output. The code template has 4 blank blocks, which are filled by the code generator, as shown in the red area in the code template. The first one initializes the memory, and the rest 3 correspond to the 3 user-defined functions. When generating the C++ code, the generator iterates the nodes in the data flow graph IR in a topologic order and emit the C++ code that will actually execute the computation. Our first optimization aim for unnecessary memory usage. We use delta-based updating on the aggregating result to avoid generating message for all edges. For operations that do not need allocate new memory space, for the result, we generate in-place version to save memory space. Second, most real-world graphs are power law graph, which means the edge distribution is extremely uneven among different vertices. This will lead to workload imbalance if each thread processes only on a fixed subset of all vertices. So we implement a dynamic workload assignment technique, which means each thread dynamically requests workload of vertices from a task pool. By doing so, we are able to get a balanced workload distribution across different threads. For experiment, we select 4 representative GNN models, which are COMNET, GCN gated GCN graph attention network. We use 6 real-world datasets, half of them with more than 1 billion edges. For baseline, we compare the performance of our system with other 3 state-of-art GNN inference implementation, DGL, TensorFlow, and PyTorch geometrics. We run all the implementation on a 24-core shared memory server with 1.5 terabyte memory. We record the execution time of our system and other baseline over different graph datasets and GNN models. All the execution time are the average value of 10 runs. The speed up is calculated by the runtime of others over the time of hours. The figure shows our speed up over other solution of GCN model, and the y-axis shows the speed up, which is the higher the better. And we get average speed ups of 10.8 over DGL, 10.2 over TensorFlow, 71.6 over PyTorch geometrics for all GNN models and the graph datasets. We also compare the memory usage of all the implementation. The figure shows the physical memory usage of for implementation of GCN over all graph dataset. And the y-axis is the memory usage in gigabyte, which is the lower the better. And we get an average memory reduction of 86% over DGL, 72% over TensorFlow, 92% over PyTorch geometrics. Finally, I will conclude this paper. First, GNN inference is an important workload for many applications, and the existing solutions for it are either suffering from poor performance or high programming complexity. We propose GIN. So we propose GIN, a compiler-based framework to generate high-performance inference kernel for GNN inference. Our approach helps us get an average 31.4 speedup over existing solutions with better hardware utilization. Thank you for listening, and thanks NSF for supporting our research.